Welcome to the session on machine learning. We have learned few basics of the linear algebra in the context of machine learning, and in this sequence we will learn few more concepts today. So we shall start with the trace operator because this is important for application of linear algebra and machine learning. So with all this knowledge, today we shall also learn about the basics of the principal component analysis, that is an algorithm development using linear algebra. So without spending further time, let us learn about the trace operator. So it is sum of all diagonal entries of a matrix. So we can define a trace operator as tr, say, of matrix A. So if I have the elements as I comma I as the diagonal elements, so this is sum of the diagonal elements. For example, say we have matrix A with elements 1 2 3 4, then we have the trace of A as 1 plus 4, the principal diagonal, and this is equal to 5. I take another example of matrix 1 minus 2 3 minus 4, then we can have the trace as 1 minus 4 equal to minus 3. So the trace operator is used in simplification of complex mathematical operations, especially when we are going to apply the knowledge in the context of machine learning. Let us see few interesting properties of the trace operator and understand it through example. So we take the example of matrix A as 1 2 3 4. However, this can be generalized. So earlier we have studied the Frobenius norm. If you can refer back to the previous video lecture, so this is basically the each element of the matrix, then the element squared, sum it throughout the matrix, and then over the sum you take the square root. So here we have each element squared, so 1 square plus 2 square plus 3 square plus 4 square, then we can take the square root of it like this. So if I take the matrix A, so here I write matrix A transpose as is equal to 1 2 3 4. So if I take A dot A transpose, which is the Hadamard product or dot product, is equal to so this is 1 square plus 2 square, then row by column product, element by element multiplication. So we have 1 into 3, then plus 2 into 4, we have 3 into 1 plus 4 into 2, then we have this is 3 into 3 is 3 square plus 4 into 4 is 4 square. So from here you can see that this A into A transpose has the diagonal elements as this. So therefore the trace of A dot A transpose is equal to sigma I A dot A transpose, the I comma ith element equals to 1 square plus 2 square plus 3 square plus 4 square. So therefore, if we compare both the situations over here, you can find that the Frobenius norm of A is equal to nothing but square root of the trace of A dot A transpose. So this holds good even for the non-square matrices. So let us check the second property of trace through an example. Say we have a matrix A equal to 1, 2, 3, 4 and its transpose as 1, 2, 3, 4. So if I find the trace of A, it should be the diagonal values added. 1 plus 4 equals to 5, and similar the trace of A transpose is again the diagonal values 1 plus 4 equal to 5. Therefore we have trace of A equal to the trace of A transpose. So this is the second property, and the third property, let us say I keep a symbolic value for the elements of A and B2 matrices, A1, 1, A1, 2, A2, 1, A2, 2, then B equals to B1, 1, B1, 2, then B2, 1 and B2, 2. So A dot B is equal to, if you multiply row by column, then you will get A1, 1 dot B1, 1 plus A1, 2 dot B2, 1. Then the first row second element of the dot product, we have A1, 1 dot B1, 2 plus A1, 2 dot B2, 2. Similarly, we can find the product A2, 1 dot B1, 1 plus A2, 2 dot A2, 1. However, this is redundant to find the off diagonal matrix. Yet I am just trying to give you a real sense of the products and the complexity of the operations. We take B dot A as, I shall take the principal diagonal elements only to save some time. So A2, 1, and we have the second row second column element as B2, 1 dot A2, 2 plus B2, 2 dot, sorry, this is B2, 1, this is B2, 1, then A2. So from here, if you write the trace of A dot B, trace of A dot B, that is equal to A11, 1, 1 dot B1, 1 plus a1 comma 2 dot b2 comma 1 plus a2 comma 1 dot b1 comma 2 plus a2 comma 2 dot b2 comma 2. Then the trace of b dot a gives b1 comma 1 dot a1 comma 1 plus b1 comma 2 dot a2 comma 1 plus b2 comma 1 dot a1 comma 2 plus a2 comma 2 dot this is b2 comma 2 dot a2 comma 2. So if we rearrange the terms, we will see that trace of a dot b is equal to trace of b dot a. So cyclic reorder is possible in this case. Cyclic reorder of matrices is possible in a trace. So therefore we can, if we have three matrices a dot b dot c, so we can have the cyclic reorder. So you will have c dot a dot b or equals to trace of b dot c dot a. So these are all in one direction, a b c, then here a b c, then here a b c. This is called cyclic reorder. This is possible just because if the matrix is not square matrix, then also it is possible to reorder. So with this basic knowledge, let us try to understand an application in the algorithm of machine learning that is popularly known as the principal component analysis. This is principal component analysis, also in short called as PCA. So principal component analysis is basically an application of linear algebra to machine learning algorithm. Suppose we have a collection of m point vectors with each point of n elements. So we have m points or vectors with each point of n elements, That means what? I am taking the n points together, x1 is a vector, m points together, x2 is a vector up to xm. So these are m points together where x is an element of r power n. So each vector has n elements. Now in algorithm we have one very prime objective, that we want to compress these points to lower dimensions to save memory at the cost of precision. So this n point vector we want to compress it into vectors of smaller length. So this is called as lossy compression, where I just write it lossy compression, where xi is an element of r power n is encoded to ci is an element of r power l with L less than n. So that is the benefit, that we are reducing the size of the vector by encoding it. So for encoding we need a function that can encode the original vector x. The function f is the encoding vector, which will convert into the vector c. So then a decoding function g is used to reconstruct the input. So if again I use a function g over f of x, then I can have the x reconstructed, but this will be approximation because information may be lost, so there can be loss of precision, and my agenda is to minimize this loss of precision over here. So in PCA, decoding function is rather a matrix operator such that G at C is obtained by operating over C through a matrix D for all Dn element of R power n by L, because D has to convert, because C is an element of L by 1, so naturally D has to be of order n by L, so that we can get x of the order of n by 1. This is the agenda. So here D is an orthogonal matrix, at least from the point of view of row to row and column to column orthogonality, because when a matrix is orthogonal, its rows and columns are normal as well as orthogonal to each other. So if the matrix D is non-square, then row to row orthogonality is there and column to column orthogonality is there. So initially we shall try to encode and then decode a single point xi, and for simplicity we write this vector xi as x. This is small x, and then because we have again decoded, we got reconstructed x. This should be with minimum error, so we shall minimize the L2 norm of this error with respect to C, and this optimal C is presented as C star. So this is a tradition to represent the optimal point with asterisk, C asterisk. This represents the optimal value. So we can write this constant as determine C asterisk such that we have the L2 norm of the original x and the reconstructed x, which we have to minimize. I write min over the argument C, so argument C over here. So this L2 norm will give the optimal value of C. Here it will be the minimum value of C, which will be the same value of optimal C when the L2 norm is just squared. Just to get rid of the square root term, we can say that this is same as this 2 squared. And now, as we have learned earlier in L2 norms, the L2 norm of x minus gc, this gc squared, should be same as the matrix or vector and its transpose, the dot product of it, like this: transpose x minus GC x. So let us expand it the right hand side. So we'll see what comes to us. This is equals to x transpose x minus x transpose GC minus GC transpose x and plus GC transpose GC, like this. So if you are careful enough, you will see that these two representations are actually scalars, because x transpose is 1 by n and GC is n by 1, so it becomes 1 of order 1. Similar is the case of the second one. So therefore, because these two are scalars, so we can use a special criteria on it. This whole transpose is same as the scalar itself. So this whole transpose means you have the GC transpose x equals to x transpose GC. So benefit of this is that we can make the second and third term equal. So this should be written as x transpose x minus 2x transpose GC plus GC transpose GC. But here we can see that when we are trying to minimize the L2 norm of x minus GC over the argument C, this is independent of the first term. X transpose T is independent of C. So if you try to minimize the L2 norm, then there is no change in the value due to this first term. So we can avoid this first term, and thus we can give the constant as argument C minimum x minus GC L2 norm square. This is equal to argument C minimum of minus 2x transpose GC plus GC transpose into GC, like this. So now we are using the matrix operator, so assigning GC as DC, or you can say that we have this constant on L2 norm as argument C minimum minus 2x transpose DC. Instead of GC we are writing DC plus DC transpose DC. So this is again equal to argument over C to minimize this minus 2x transpose T DC, plus if you break it, then you will see that this comes C transpose D transpose D dot C, like that. So now to understand the nature of D transpose D, let us take an example. We have, however, non-square D is possible. We have 2 by 2 D, 0.6, 0.8, minus 0.8, 0.6. So this is an example of orthogonal matrix. So it means the D transpose is 0.6, 0.8, then here minus 0.8, then here 0.8 and 0.6. So D transpose D is equal to 0.6, 0.8, 0.6 with 0.6 minus 0.8, 0.8 and 0.6. If you multiply, you will get element by element product, 0.6 square plus 0.8 square. Then we have 0.6 into minus 0.8 plus 0.8 into 0.6. Then you have minus 0.8 into 0.6 plus 0.6 into 0.8. Then minus 0.8 square into 0.6 square. So this will be solved for 1001. So D transpose D is a identity matrix of the same order as D. So this I can write as I2. So it is equally applicable if D is non-square. So with this information we can write argument over C to minimize x minus gc L2 norm squared is equal to argument over C to minimize minus 2x transpose dc plus C transpose. Here instead of D transpose D we should write I, but because D transpose is of the order of n by L and D is of the order of D transpose is of the order of L by n and D is of the order of n by L, so the identity matrix should be of the order L by L, that is L. So I should write here IL and C. So you have to pause the video and try it yourself to see how correct it is from your side. So this can be written as argument minimize C, and this is minus 2x transpose dc plus C transpose C. So now we need to find the gradient, because C is a vector, so we have to minimize in terms of C, so we have to differentiate with respect to C. That will be the gradient vector. So the gradient vector is definitely a column matrix, and here we can write that a gradient vector grad C over this norm, so minus 2x transpose dc plus C transpose C equal to 0 has to be achieved to obtain the desired condition for minimizing the error between the actual point, which is in the form of vector xi, and the reconstruction of x. So in the next video lecture we shall go further and find out the both quantities how this can be operated by the gradient operator. So friends, if you find this video useful for you, like this video, subscribe the channel and set the bell icon to get the notification of updates. You can always write me your queries through my email id machinelearningbasis@gmail.com, and my students can send me queries through WhatsApp. Thank you for your patient listening.